Okay, well, it's really been a pleasure to hear all the wonderful talks today and all the exciting work that's being done. And I have to tell you that I've only known Bauman for less than a year, maybe 9 months, about 9 months. And when I learned about the work he was doing, I was just very inspired by it and thought, gee, you know, we ought to be doing this in school. Everyone talks about how inspiring this is and how much fun it is to work with these wonderful images and ideas. In our work, we have followed children building mathematical ideas over a long period of time. In fact, our longitudinal study is now in its 21st year, where we follow the same group of children where we gave them mathematical investigations to do that was not part of regular school. And I was very excited in George's presentation right before this, when he showed Pascal's pyramid, to tell you that one of our participants in the longitudinal study, Kevin is a part of this as well, actually built those ideas over time, starting by playing with little plastic cubes and solving counting problems, and representing those ideas not only spatially, but representing them and making the connections symbolically. And that's really very exciting to me to see how that can be built by a student. And it seems to me that there's a lot of work to be done because you have all these wonderful ideas, and the challenge to all of you is now, how do you make these ideas accessible to children, starting with very young children? I'm talking about very young, age-appropriate, related, fun investigations, and bring in the appropriate mathematics and the symbols and the different ways of representing these ideas and working with them. And I think that's really a challenge for all of us, and I think especially there's a great need because spatially we've lost so much of those representations in regular school, which is pre-K in our country at least. So inspired by what I've seen of Bauman's work just recently, I said, gee, you know, Kevin would love to see this. He's very excited about these ideas, and he teaches these when he can, and he's now teaching a discrete math course for teachers for us now, and they do a lot of investigations with these ideas. So Kevin immediately said, this is wonderful, I want to try it. And so Bauman very nicely let him have access to the software, and Kevin introduced the software to our grad students. And I said, well, Kevin, you know, what do the students do with this? And so Kevin was really wonderful. He went out and said, okay, well, I'll actually videotape my working with a student who will never have seen these ideas before, but has studied enough mathematics at the high school level to deal with finding roots of polynomials and so forth. And let's see in about, what, an hour session at most, what might a student do during this session? So we're going to tell you the little story of what this student did, what was the challenge. Kevin started by challenging the students to find roots of a set of polynomials. I think there were 10 of them, of a variety of degrees. And all of these polynomials had real coefficients, and but they had complex and real roots. So in the investigations of solving these equations with the mathematics they know, they had learned in school, mostly symbolically, wouldn't you say, and mostly by doing whatever graphing representations they could with the ones with real roots and some complex. So this is the story. So I'm going to move back, and Kevin is going to tell you the story of this. I'm going to stop all of this, the overview, because I think I've said enough that's appropriate. But I want to tell the story right away, and then we can come back. Because my interest in this is really, as a math educator, to study in detail how mathematical ideas are built by students. And how to do this is, I'm going to throw the challenge right back to all of you after he's given his discussion, and I'll tell you a little bit how that fits in. So let's talk about the case of Ankita, which is, how old is Ankita? Would you say about 17 years old?
Yep.
And she's a high school senior. Okay.
So I first started with a couple. I wanted to try the lesson out with a couple of classes, and I had them look at the screen, and I started. Was kind of trying it out just to see what polynomials would work best, or what I needed to add, and what I needed to take out. So the videotape of Ankita went on for about 50 minutes, and it was 7 polynomials that we got down to, and this is the order that they flow in. Here you have 2 real roots. On this one you have 3 real roots. Here you have 2 purely imaginary roots. Here you have, let's see, 2 real and 2 imaginary. Then here, we talked about this one earlier today, where we have 1 pure real and then 2 complex roots. And this one, also 1 real, 2 complex. And then finally down here, where we had 4 imaginary roots, purely imaginary. And I like that whole discussion of, of what's imaginary and what's not real. So 16 minutes into the discussion, she's been looking at those problems and working on the problems, and she's looking at this point at the relationship between these two. While she has a plain sheet of paper that she can write on that has the 7 polynomials, and I had printouts of each of the polynomiography graph, the polynomiograph. Polynomiograph, yeah. I'm losing syllables in there, or adding extra syllables. So she's got a printout of each one so that she can look at them quickly, but she also has my laptop in front of her so she can type in and look at them as she wants to. So she makes the observation that these two look similar. One looks like it's tilted on its side. They're not opposites, but they're similar, is how she puts it. And I should also add, she is in multivariable calc. So this would be like a 3rd semester calculus course. She completed calculus as a junior. I had her as a sophomore in my pre-calculus class. So she is now 2 years past pre-calculus, where I know in my class she had a discussion about the complex plane, but I don't know that there was much discussion since then. So with those two, she has these two, this is her handwriting. Up here, at the beginning, she wrote down x-axis and y-axis as zeros. And she erased them and wrote that down, and I asked her to stop erasing it so we could have a record of everything. But she has difficulty at this point even calculating the x and y intercept of these the 2 polynomials, and my guess on this would be that she has not seen anything like this in a couple of years, because she's into all kinds of different series and integrations and stuff like that. So it's not at a level that she's used to working at. She did have difficulty in the beginning coming up with if x equals plus or minus the square root of -4, what that answer was. But she was in 3rd semester of calculus at the same time too. So she did draw after a few minutes after that work. She did draw this, which is like a traditional representation. If she types x squared -4 into the calculators, they all work on the Texas Instruments calculators, and hits graph, then this is the image that's going to come up in the calculator, and that's the image that she associated with that polynomial. So 17 minutes in, she starts to speculate that the degree of the polynomial has something to do with the number of colors that she's seeing on the screen. In here, she, even throughout the whole exercise, was unable to factor this. Even at one point I asked her if she could remember how to factor by grouping, which is a technique that's introduced in, certainly in Algebra 2, so it would have been 3 years prior, where if you factor x squared out of those two terms and the -1 out of those, then she could have, but then pulled out and gotten x squared minus 1 times x minus 3. So she would hopefully then see that the roots are 1, -1, and 3. And then over here, she eventually came up with some interesting ideas that I'll get to in a minute. So she's looking at this and speculating, oh, right, we have a third-degree polynomial and we have 3 colors. Based on the size of the window, because this is, I believe, the y-axis would fall right about there. The x-axis is going to go straight across here. The darkest region here is going to be -1. That's +1, and then the dark region on the blue will be +3, and those are the 3 roots. And this is the graph for x to the 4th minus 16. Maybe Bobby can comment. At one point, this area appeared yellow on hers. Is there? How does the color selection go?
It might have been some problems with the demo, but I mean, you should get 4 regions here.
I don't know. We got 4 regions, but it was just a different arrangement of the colors. Yeah.
As a guess, I might say that, well, the color normally depends on which root is encountered first. So if you start with -c plus 3i, then you will find one root first. If you slightly zoom in or zoom out, because of the complexity in the upper left region, you will find another root first, so that will be yellow.
Yeah. But she made that observation. She's like, oh, it's 4 colors, but they're in a different arrangement. So here's her work, and you can see she is trying to do some kind of factoring moving around. But she does associate. This is a cubic, so this is what the calculator is going to give me. She's got, she knows that it crosses the axis here at 3, and she didn't comment that -1 should be one of the roots. But she also has 2 different graphs there, so I'm not sure if she recognized it. Fairly confident that she didn't recognize until she was associating with the colors that this is 3 real roots, which would be the bottom line, and then the top line has 2 complex roots and the 1 real there. And then as she's working through here, she starts to make the connection that this one can be factored into those 2, which are, so the 4th polynomial on her sheet can be factored into the 1st and 3rd polynomials. And she does plot a couple of points there. There's -2 and 2, and then she must plug in 1 and -1, and then down at the y-intercept there would be -16. So 28 minutes in, she's recognized that the product of polynomial 1 and polynomial 3 is polynomial 4, and she starts to make the connection that this graph times that graph is going to equal that one. She didn't quite understand why, but she knew that algebraically that was going to happen, so that's where she saw the pictures. Then she moves on to the 5th, 6th, and 7th polynomials, and she makes the observation that the 5th and 6th, which look like this, are rotations of each other. Here's the real root 1, and this one has the real root of -1, and then this is like a half plus or minus the square root of 3 over 2i. This is nice in some honors pre-calc books. they have a discussion about the nth root of unity and how you're taking 3 roots of radius 1. And so they'll be mapped out perfectly at 120-degree rotations. And I find this to be a nice representation, a way of explaining that to the students. If you run, x to the 5th minus 8, then you're going to take, that's a bad number to pick, x to the 5th minus 32, then your radius is going to be 2, but your roots will be at 72 degrees from each other. And you do come with those to get pairs that she recognized she should have because of the quadratic formula. So here's some of her work. She knew that this one would cross at 1. At this point, we're having a discussion about whether or not she remembers the complex plane, and that's when she writes down the real and imaginary, and she starts forward. And then 36 minutes in, I asked her to several times to discuss why some of the, in this, I'm going to go back, why some of the reasons were darker than the others. You can see it a little bit better in this picture, why this area is darker than, say, the blue there, or why this green is darker than the green over here. And she starts to think that this may have something to do with the solutions to the polynomial in the complex plane. And she came up with the answers plus or minus 2i and plus or minus 3i, which on this graph are going to be represented by the y-axis is going to go right down the middle there, that's the x-axis across there. So 3 and 2 on, that represents 3i, 2i, negative 2i, and this would be the 3i down there. I'm sorry, the minus 3i at the bottom. And so then I asked her about the why, say, that area there is red, and why it wasn't blue. And I showed her the little button that allowed her to track the path. And she started playing around with it a little bit, and here's one of the diagrams that she came up with. And she made the observation that red always moves to another red. And that's, I really like that. And I also like the discussion earlier about paths, because I started thinking, when it was going on, I looked at what was going on up here and the diagram of the paths that were on the map. And I pulled out, because it looked just like this to me, I mean, this could very well be your errands for the day. It's really interesting that the definitions of the word path and how we could use them. And I wonder if we could have kids graph all their where their classes sit in the building, and then generate a picture based on where their classes are going to be for the day or something. So she starts to then talk about, now this is a student, yes, she's in multivariable, but she's never had any kind of discussion about iterations. Everything has been functions and graphs of conics, but nothing where you take the y value and feed it in and it becomes the x value. So she makes the observation that you follow the answer, you just keep plugging it back in. So she knows that she takes that value, she plugs it into the polynomial and gets this one, plugs that value and gets this one, plugs that value in and gets that one, and keeps going. She knows that I plug this in, I get this. The smaller one goes to the bigger one, which is really interesting because a couple days after this interview with her, we were meeting with Bauman, and he started telling me, I didn't understand why the whole complex plane worked, but it's ponds, Is it the ponds or the pools?
sorry?
The ponds or the pools, where this one,
Oh yes, I mean those are the red represents the region of convergence to the root,
right,
to one of the roots.
right, and so
And those are like, yes, little lakes. They are.
and so there are, for this one, this is the X to the fourth, so there's 4 of these little lakes that feed into the next size lake?
Yeah, there is like, that's right. That would be, yes. I mean, in a way, each, if you look at the big basin of attraction where the root is, that's like one big lake.
Right.
And then there is maybe one lake that pours into that, but then from then on, you could have 4 lakes, 4
Right.
regions pouring into one. And
Right.
each of those regions in turn will have 3 lakes that pour into it.
Right, and that's what the small ones do, right?
That's right. Those
Right.
are like
So
they are
that-
pouring
yeah.
they're pouring down to other little lakes in the hope of getting to the big basin of attraction.
Right, and I think, I mean, that's how I interpreted what she was saying, that the little one moves up to the next biggest one, moves up to the next biggest one. You know, if we had multiple sessions, you know, maybe she starts to understand it more. She still hasn't worked with a polynomial with complex variables yet. You know, and by yet, I mean, I didn't introduce it at all either. And she makes that observation that every iteration of a color stays in that color. So red at, like, say, this level will never bounce over to the blue or into that blue or the green, or red will stay in red as you iterate it over and over and over again.
I'd like to point out that Kevin had a little time to play with the technology, really not a very long time, and kind of enjoyed it. And then he introduced it to others and then followed through with his student. And I think it's amazing in this little piece of time how the student was engaged and interested and what the student was able to observe. And I think that there's great potential here. I mean, these are tools that I'd love to see in the hands of lots of teachers. And I'd like to see in laboratories where students could go and investigate and play and observe and notice these things and actually create these wonderful images. And I think the challenge to us, I mean, we know that students need to have these graphic representations. They need to be able to coordinate their symbolic representations in graphic, and I think we have it backwards in school. I think we start symbolically with even very, very little children, unfortunately, unless they're in very special situations where they really get a chance to deal with more spatial graphic ideas. And we know they can connect them. The research that we've done at Rutgers over the last 2 decades, when opportunities are there and when there's the freedom to explore and to investigate and to collaborate with each other and to talk with each other with ideas, under those conditions that I think we all believe are opportunities for creativity, students do have powerful ideas. And there's no telling where they can go. I was sitting back there just chatting with one of my colleagues just a few minutes ago, and I was saying, it would be a wonderful book just to interview all of you, to try to follow how you yourselves came up with your ideas. You know, what's your personal story? You know, how did you become engaged in what you become engaged in? How do you explain from interest and passion for what it is you've been doing? When I think these stories are important, that's why I want to thank George for putting what he will on the website for people not to forget this, because we're leaving too many students behind. And I really think there's a lot of work to be done. So from the I guess the point of view of an educator, Kevin and I are educators, the challenge is for us to make it better for the next generation. And so thank you very much. Thank you, Bob.
I have several comments. One is I'm very happy to see a case study research, because I think that this is really the fundamentals that we need as educators is to see what an individual does. We don't need more data than not telling us as much as the case study is. I teach a number of college-level freshmen at a smaller university, and I see Anika's calculations, and they're the same types of errors that I see as I'm grading papers. Although I can see from what you told me that she is, Nikita, that she's already an advanced student, so that's very refreshing. I'd like to know whether she's going to become a scientist or a mathematician.
No, NYU started going into business. But I tried to convince her to use complex numbers in business.
I can only tell you, all of you, that the text is still being written. We follow the same group of students. Now we're in our 21st year. And any time along the way, we would ask them what they want to do, what was their interest, and I don't think they really know, and they change their mind as we do too. And they do interesting, wonderful things, and I don't think that any of the, I think the opportunities are much more available, richer ones, if they have had these experiences earlier. Whatever they choose to do or major in is not even something that they own. They may be doing this for reasons other than what's their passion. And they change.
I'd like to also mention an impression that I have from looking at her work, and that is there is a confusion of the two planes, the plane in which she's graphing the function and the coordinate plane in which the action is happening. And some of that confusion might be moderated by observing that the complex function of the complex variable has a graph itself, and that graph is not immediately visible to us in the three-dimensional world.
Thank you very much for that comment.
May I ask that the next speaker starts preparing while you're asking that question? So we wait 5 minutes.
Okay, thank you. Because I think we try to avoid this conflict, to call the plane not complex plane, which is real. The plane is just real, and the image is real. Because the complex numbers are only one dimension. So we call it the Gaussian plane. And so we avoid the confusion of the students when they learn about algebraic geometry and really have to make a complex plane out of the complex extension out of the real plane. So there is a confusion, and we try to avoid that.
So the question is, I don't know what the language is that was used in high school. Do you make a distinction between Gaussian plane and
No, we never mentioned the Gaussian plane.
I think the textbooks themselves are part of the confusion.
I think just calling it the complex plane scares them. Because we said it was like the friendly plane.
Well, I want to say that we think about
complex plane can be given the structure of the quaternion.
I mean, I really don't believe that the fact that we are going in this thing and mapping from R2 into R2 with a four-dimensional space is something that is going to enlighten the students, from my experience. I believe they see what is happening, they have an understanding of the things happening in the complex plane, and they also understand, the typical graphs. I mean, we look at a graph, the usual graph, the number of intersections is the number of roots. If you look at this polynomial graph, the number of colors are the number of roots. So there is a correspondence of, different types.
Yeah, but I think my point is that even with the software that you have now, you can sketch the surface, which I would call a surface because I'm a topologist, not a geometer. But you can sketch that surface from 4 space, project it into 3 space, and move around the picture, and you will see the graph of those polynomial equations, and you'll see another similarity there.
But I think too, it goes to, like, say, x cubed minus 1. Well, that's x cubed equals 1, and we tell them how many, what's the cube root of 1? And it's 1. But we don't tell them that there are 2 others. And we do that. We hide the truth from them to not scare them when they're, say, 13 or 14 years old. So yeah, I think there has to be that graduated approach to it. And I think this can help. I think they understand a little bit more. It's another representation, a way to maybe it connects some of the kids that can't get from one picture. But I don't know. But
I still think it's adults who are afraid of abstraction of the children.
Yeah, right.
Well, the whole problem goes away if you just teach them about 2 by 2 acres. How to add them, how to multiply them, how to divide them when you can. And it's not that hard.
Not that scary.
I would also say, why don't you teach them group theory or something that they can hold in their hand and notice that there's only 2 kinds of finite elements. If you have 4 elements, there's only, I mean, help me, I'm not the greatest group theorist in the world, but there's the fear group and the C4 group, right? Isn't that the only 2 ways you can combine? Now that's something an 8-year-old can understand or a 12-year-old. I don't think you're going to help with it. You just said that the cube root of 1 is 1, and we don't tell them that there's 2 others. But the facts are you demand that they understand that the cubic polynomial has 3 roots. So you're already squeezing the kid between a vice. There's 3 roots, but there's a. So you are you're lying to him the whole time.
Yeah.
I mean,
I always, when we start that lesson on the Maher theorem and the nth root of unity and finding the 3 complex numbers that have the 3 complex roots of 1, I say, what you're about to learn is that all your math teachers in history have lied to you.
well, that's what my American history teacher said too. When I finally got seriously, when I finally got a good American history teacher, who wanted to tell me the truth about how this country got here.
The answer is that good teachers don't want to lie, but often the elementary school teachers don't know. And they often don't want to know.
No, but an elementary school teacher can understand that there's only 2 ways to combine 4 elements. Let's start teaching them, and I mean teach the grade school teachers even, something that they can understand. Because the goal of math education is not math. The goal of math education is a way of thinking.
Yeah.
Right?
Yeah.
So it doesn't matter. I mean, this poor girl, she's in her 2nd year of calculus, and she's confused by y equals x squared minus 4?
Yeah.
Where did we go wrong?
Yeah. To some extent, it could have been that whole, white coat, syndrome where you get your blood pressure goes up in the doctor's office. But
I doubt it, Kevin. I really doubt it. Because if you look back at the curriculum, you look what the students are lectured to. Students are taught algorithms. Students are taught rules. They're only expected to give symbolic representations of results. And they're not asked to think about the meaning behind it. And we're shortchanging them. These are very talented students, so we're shortchanging their teachers.
They're also tested to death.
They're also tested to death, absolutely. And they pour, and more is poured into the curriculum, and there's no time to move back and to think and to reflect over time. And you don't have to do it a whole lot. Our own research has shown that you just need to give time for students to be thinking about what they're doing and building up the ideas and the representations and making those connections. We're really not talking about, rocket science here. This is having a respect for each person and the individual about what they're capable of learning. And so you look at the time you spend on Calc 2, Calc 3 with learning this procedure, practicing this, this example and that, when they haven't had a chance to think deeply about anything. I think that's our real problem. So you're absolutely right, and I think that the kids deserve more. We could do more, and I really think this is another foot in the door, especially in high school. I mean, it's harder to get into high school and to change things around. Guess what, guys? Where do they get their models for teaching? High school teachers. Just think about it. And they think that's what they're supposed to do. At least the elementary school teachers, when they begin to understand something, they are willing to make changes. They really are. High school teachers, they can't. You said it, testing, testing, testing. Right? That's the expectation here. So there's a lot of work to be done. But I really think together it can be done. I'm optimistic. I don't want to leave this on a pessimistic note. This is 50 minutes. You analyze this, you interview her, you find out, you give her, she could build this up in a relatively, she's a bright child apparently who has a lot of gaps and holes. Now how do you fix it, right? How do you do better? I think that's the challenge.
I think, for example, in Austria, we actually, till the economic crisis started, we had a big lack of engineers. And why? Because there was lack of interest in mathematics. And very similar problems that you talk about. And I think that it's very, now it's a little bit changed because of the crisis. Actually, this is a positive thing of the crisis. But on the other way, I think it's very important. For me, it's interesting to hear that here in the United States, you have the same problem that we are fighting in Europe. I mean, now it's all the PISA test and the PISA test, and actually it turns off all possibilities to think. And what I very much like your sentence about mathematics is a way of thinking, because it's actually what's also design talks. It's from Nigel Cross, the book from the 60s. Design and the way of thinking is now all reprinted again, and it's design and the way of thinking, which is not a way; it's a way of living. If you understand it, it's part of your life.
I think what you said about giving them time to think is very important. And neurological changes have to take place within your mind and body or whatever it is while and after you're learning something. In a former life, I taught lots of math, like calculus. And at one university, they have this kind of split semester system, and you're supposed to teach these kids calculus in a split semester. Well, this is like taking a class of students who are supposed to learn all the Bach etudes, in a split semester. It's not going to happen because they have not developed the physiology and the neurology. Whenever a mathematician is confronted with a new problem to solve, whether it comes easily or not, especially hard problems, then there is this period of time when your biology, your neurology has got to catch up with this problem. And that takes time. It's no different than learning how to play a musical instrument. You just cannot cram it into the last week. Same thing.
Okay. Carolyn, for your next book with the interview, just a hint for you, there's someone from their concert sitting there.
I think it's a great idea. I really do. It was like the other George's book, the 1001 different. I think it's, we need to hear stories.
1001 interviews.
1001.
Okay. We thank Kevin and Carolyn.